Right. Thanks for the organizers first for organizing this wonderful workshop. It's been a pleasure to be here. And so today I'm going to talk about this series of results that we had about how to use functional approximation, or like how you can use functional approximation in generating reinforcement learning. What's the utility of having functional approximation in reinforcement learning and all that. So first I want to thank my collaborators. It is Gellert. He's discovering that this world is embodied from above, and you can see the joy on his face for seeing this. And he's at DeepMind, and he's also a PhD student at UCL. And other collaborators being Philip, who is a PhD student with NAN. NAN is also there, and Barnabás Jancer, who is a PhD student in Cambridge. Yassin and András are at the Foundations team at DeepMind. Okay, so I want to start by going back to the year of 1963. Probably none of you were alive at the time. I wasn't. So I don't have direct memories, but it was a fantastic year because this paper was published that year. Nobody really knows about this paper, but it's kind of interesting to go back to these old papers. This is a paper by Richard Bellman, Robert Kalaba, and Bela Kotkin. And the title is Polynomial Approximation, a New Computational Technique in Dynamic Programming, Allocation Process. So I want to use this paper as a precursor to explain to you what this functional approximation business in reinforcement learning is about. It's kind of, oh, my animations are gone. All right, anyways, never mind. So it solves a what they call an allocation process. It's a very specific instance of you can cast it as an MDP. You will see that it's casted effectively as an MDP. And so what is this? You're given age different utility functions, and they correspond to age different projects that you want to allocate resources in between. The resources are d-dimensional, and a resource lives in this hypercube, in this d-dimensional hypercube. So you want to split up your total amount of resources into age different parts such that you're maximizing the total utility. How do you do this? Well, dynamic programming was invented for doing things like this. So you can imagine pictorially that these are the nonlinear utility functions, and you are at some stage age, and you're trying to make a decision about what to do there. And so far, you decided to allocate this much of the resources S. So this is one dimensional so that I can draw it. And as you go, you can imagine that from this point on, things are going to go on optimally. So you can define the optimal value achievable in the remaining period, so for the remaining projects, given that you have already used up this much resources. And it's not hard to see. And this was kind of like the thing that Richard Bellman was actually exploiting in many different ways, that these optimal value functions satisfy this recursion, right? So the optimal value function for some stage is a function of the optimal value function of the next stage. We just have to think about that. Okay, how is the optimal value for this stage? Well, I need to make a decision for this stage for the remaining resources. So I have to subtract from the resources I have, but I've already spent. And so this is the interval where I can make a decision. For that, I'm going to get a payoff for this project, and I will also consume some resources, and I will end up somewhere else, and I will continue optimally from that point on. So because of the additive structure, the optimal value is going to be the sum over these two things, and you just have to choose the best action for that stage. And you have a boundary condition for the final stage as well. And the question that they are asking in this paper is how to compute the optimal value and specifically what is the allocation. It's a very simple problem. And this looks beautiful. And they're thinking about, like, they were trying to solve this for specific cases when there is some extra structure, but they saw that like that doesn't quite generalize very well. So they turned to numerical solutions. So they were thinking previously about discretizing basically this state space, discretizing the action space, but then they noticed that, well, if you discretize a d-dimensional space and you want to have some good accuracy, then your resource needs for computing this thing are going to blow up exponentially in the dimension. So the question is, can we do something about this? And so this is what this paper was about in 1963. So what they propose is very simple. So go back to the one-dimensional case. Maybe the state space is just this -1 point. Here, well, change it a little bit. You can imagine that you will have some basis functions. So they're thinking about, orthogonal basis functions of various kinds. And you are going to linearly combine these basis functions to represent the optimal value function in an approximate manner. And then somehow you plug this into the recursion that we had before. So what does this do? So what's the new idea here? The new idea is that we are, well, okay, like this shouldn't be D. That's a different D. The new idea is that we are decoupling the dimensionality of the state space from how many basis functions we are using. And if you have a good guess about kind of the smoothness of the optimal value function or what basis functions are going to capture the optimal value function well, then maybe you can get away with just using a few coefficients, and all that you're left to do is to discover these coefficients for, okay, you have to do it for every stage, but that's the only thing that you have to do. And so that's indeed what they propose, and they have, so we have this recursion, and they call these successive approximations. You can write it with an operator notation as well. And then they just have this idea that we just have to plug in these basis functions and somehow calculate the coefficients. And then the question is, okay, if I have coefficients for the next stage, how do I get coefficients for the current stage? And specifically what they propose is that, well, you just do this calculation in some way, this successive approximation at some nodes, at some points, and then you extrapolate or interpolate, you just solve a function fitting. So this function fitting is going to basically project this function into the span of the features. So that's what they propose. And today we would recognize this as an instance of fitted value iteration. So in reinforcement learning, this is what people call fitted value iteration. So they use this, I don't know, Ottoman norm basis and Gaussian quadratures for approximating the projection because they're overqualified for this job. We would just use Monte Carlo. All right, so what are the results? Any good paper has to have some numerical results. They had two-dimensional problems. They were very happy. They calculated, like they had nice tables. And they conclude that if they combine these techniques, polynomial approximations, Lagrange multipliers come in because you have a constraint action set. With that of successive approximations, there should be very few allocation processes which still resistor. So they're kind of ambitious but modest at the same time, right? Like allocation processes, but it's there is definitely optimism there. All right. So why the optimism? It's because they kind of think that they figure out how to avoid discretization. So no curse of dimensionality. So Bellman coined this term curse of dimensionality due to the discretization. They were really not a fan of that. Okay, so there are two questions that arise. And the first question that arises is the question that I defer to our colleagues in the econometrics and other departments. So there's the question of like how to choose this polynomials or how to choose the basis functions to approximate the optimal value function. And I rather want to focus just on the computational aspect of the problem, which is that if someone already chose some basis functions, can we really use these basis functions to get these coefficients and get the optimal value, good approximation to the optimal value, or get a good policy fit? In particular, so we're going to have MDPs, they're finitely many actions, so that's going to be a simplification compared to what they were doing. So A is a number of actions, H is going to be number of projects or number of time steps, horizon. D is the number of features and some accuracy, epsilon that we desire. And we ask the question, are there algorithms out there that are able to deliver this accuracy regardless of the size of the state space? That's the question. All right, any questions? Okay, so the problem is clear. Good. So we are done with the first two parts. Just one slide with some notation and some terminology, because, well, I will need to rely on some of this. So we're going to be more ambitious, look at MDPs. It's not allocation processes, but it's a very close relative. We're going to have states. So we have the Bellman optimality equation as before. We're going to have states. We have actions. They're in a feasible set. But I'm going to simplify, and a feasible set is always going to be the full action set. Don't think that at this moment, that simplification is, I think, tolerable. For every stage and every state and action, if you take that action in that state, you receive an immediate reward of R. And then you transition to a next state, which is a random next state. So there is some randomness acting on a transition. So this is a transition function. And then the optimality equation looks like this. And so one little innovation that, well, okay, it's actually quite a nice thing that comes from the machine learning literature. Chris Watkins' innovation is that, well, this right-hand side, if we just add these two things together, you can call it the action value of choosing action A in this state. And sometimes it's very beneficial to directly approximate the action value function. Why? Because if I knew the action value function, I would know how to act optimally. Yes.
Sorry, could you go back to slide 3? The realizability assumption for all value functions or just the optimal one?
We'll come to that. There will be a whole discussion about this. Yeah. So this is just for now notation. This is clear, right? So one more notation is that. I'm going to drop this notation for most of the time. In the MDP literature and machine learning, you usually have just a transition cutoff. And my notation is going to be that, like, if you have a state S and an action A, then this is just a probability distribution over the next state. So I can write something like the index product of this probability distribution with a value function that gives you the expected value that you're going to get if you transition accordingly. Okay. So just so that I can simplify some notation. All right. So yeah, back to the content. So we are done with these first two things, and I told you in the panel you have to concentrate on algorithms. So I'm going to focus on some algorithms. So I will talk about optimistic constraint propagation, which is an algorithm by Jen Wang and Ben Van Roy from 2013. Which is addressing this problem in the deterministic setting. And then I'm going to talk about a bunch of other algorithms under misspecification. And then I will talk about results that I call weak functional approximation results. And that's going to be the bulk of the talk, actually. All right, we're done with this. So the first part is this optimistic constraint propagation algorithm. This is for deterministic algorithms. Deterministic MDPs. So we have these basis functions, and we want to figure out what the coefficient is. The coefficient is shared between all the stages without loss of charity. And if you make this assumption, then you can plug in your function approximator into the Bellman equation. You can subtract one side from the other, and then now it becomes a root finding problem. So you just want to find this theta parameter that makes what we call the TD error to be 0 at all the state action pairs. So we have a bunch of constraints. If we find the right constraints, maybe we can just find these equations. Find the root for these equations. So the TD should be 0 at all the stages and all the transitions. So we're going to focus on trying to shrink the parameter space. So initially we are ignorant. We don't know the solution. All the thetas are possible. So what we're going to do is that we're going to start with all possible parameters. So we assume that the true parameter has a known L1 bound, B. It lies in this version space. And we're going to iterate. And in every iteration of the algorithm, the first step, we're going to choose an optimistic parameter. So what is the optimistic parameter? It's like definition of optimistic parameter is that like if this parameter was the true parameter, we would get the highest value at the initial state. We have some initial state. We are running. We're going to run experiments from there. So it's like online learning. And then once you have this parameter, you can just like do as if this was the true parameter. So it's going to be verification. We are going to generate a bunch of new constraints. So we roll out with the resulting policy up to the end of the trajectory. We collect all the data that, so we collect basically a trajectory. It's deterministic. So there is only one trajectory up to the end. And then you can measure these TD errors along the trajectory. And you're going to enlarge your constraint set by adding the constraints that all these TD errors need to be there along the trajectory. So you potentially shrink the version space, and you're going to stop when you cannot shrink anymore. So if you ever find a trajectory such that you're not shrinking the version space, then you stop. Well, you need to ask the question, is this computationally efficient? Yes, you can implement this computationally efficiently. And the other question is this going to really work? Is this going to return an optimal action? And so that's the genius of these two gentlemen. They show that it is. And I will later show you an algorithm that generalizes this algorithm. And I will explain a little bit more at that algorithm about like why this algorithm works. Okay, and then you will understand. Okay, clearly, if this other algorithm works, this must work too. Yes.
This algorithm works is you're not doing any of these steps, right?
In the initial, I think that you need maybe a little bit more. So this is just online, right? So I only need to have the ability to execute trajectories. But the initial state is random. Then I think it's a little bit more delicate. Like you will need to add extra stuff, but you can accept it.
I missed the beginning. So is this equality, the first one, the quality function is phi times theta star. Is that an assumption or without loss of generality?
No, that was the assumption. So that is what Bellman told us, that we have these basis functions and then you just need to find the coefficients. And then now we are asking a question, can we find the coefficients? Yeah, absolutely. Good question. All right. Okay. All right, so they proved this theorem that for any of these theorem systems, blah, blah, this algorithm stops and its body time and body number of queries are sent to the environment. All right, this is great. So this was, by the way, like 50 years after Bellman's original paper. There's been a lot of other developments, but somehow like this question was not really thoroughly looked at. And even in the interim period, people were busy with other things, but 8 years later, this paper by Du, Kakade, Wang, and Yang appeared, and that inspired us, among others. And this then sparked a number of other results. And so now, basically, I want to tell you about all these exciting developments that happened since then. All right. So the setup of this Du, Kakade, Wang, Yang paper, it has a lot of different results. It is basically the paper that starts to ask these computational questions and query efficiency questions in a very clear language. So that's a big contribution of this paper. And so one of the setups that they look at is that you can, if you have a policy, for each policy, there is also an action value function that describes how much this policy is going to make if you start it in a state and you take an action and then you follow the policy. Okay, so that's the action value function of the policy. And one of the setups in the paper is that they assume that for all the policies, the action value function lies in the span of the features up to an error of epsilon. So that's the approximation error, and it's a uniform approximation error. And the genius of this is that they start to ask the question, like, even if like we have this much stronger assumption, so it's strong and weak at the same time. It's a strong assumption because no, for every action value function, for every policy, we assume that the features are good. So the features are good for many different things. But there is some residual error. So there is this epsilon uniform approximation error. So they ask a question, under this setting, is it possible or not to come up with a query efficient algorithm, an algorithm that would, like, just go in the MDP, and there are different query models. So here they consider the generative model, or I call it random access model, or global random access, where you can poke any state action pair and get a transition from there and get corresponding reward. They ask the question, is this possible? And then they prove that this is not going to work. So if you have a target accuracy of delta, and this target accuracy is not low enough, is not high enough. So if the target accuracy was compared to the approximation error is inflated by a factor of square root of d, then you may have a chance of having a polynomial algorithm. But if this is not the case, then you have no chance. So that's kind of like a big wake-up call for everyone who was hoping for something much better. Because it seems that, well, on the one hand, we have uniform approximation errors. So there's like L-infinite errors. They're already big. And no, if you're not inflating those by a factor of square root of d at least, then there is no hope for a computationally efficient solution, because there is no query efficient solution either. All right, so this was very kind of innovative at the time. And you can pair this with a positive result that says that, well, okay, if your target accuracy is exceeding this critical threshold, then polynomial computation is available, and that's what we were doing in our paper. Because to have both sides. And so what's the insight here? So the insight is that in reinforcement learning, you really need, or in this MDP calculations, you really need to deal with uniform approximation errors, because you're looking at like maximum values, the optimal values, and some of they pair much better. Like they kind of force you into this just working with uniform approximation errors. And these uniform approximation errors, if you're only making so many measurements of a function that is just nearly realizable, then they can blow up. So extrapolating from polynomial many queries without blowing up the approximation error by a factor of square root of d is just information theoretically not possible sometimes. So caveat is that this is specific to some choice of the basis functions or this feature map, as we call it in machine learning. So you can choose much friendlier ones where there is no blow up. Okay, so that's an interesting direction maybe to try to understand what's happening there. And so now back to Emma's question. So what are the assumptions that we are making? So there are a bunch of assumptions like that you could make, like this one that I talked about, that all policies action value functions lie in your function space. Or you could make an alternative one which says that under the Bellman optimality operator, this function space that's induced by the features of the basis functions is closed. So there are these assumptions concerning the features, I call them the strong assumptions, right? Because no, the features have to do a lot for us. We are asking them to do a lot. And the weak assumption is what I think Bellman and these other people in the early days had in their mind, that it's only the optimal value function or the optimal action value function lies in the span of the features. So there are these two alternate ways of thinking, but here we already saw that if you add approximation errors, then unless you're willing to explode those approximation errors by this square root factor or something that depends on the features, there is no hope for query efficient algorithms. So that is the question of like, okay, here we are assuming even less. Can it work? Well, the errors need to be blown up, or if you're interested in negative results, or like we think that maybe the results are not going to be positive, then you can ask the question, okay, what if you have exact realizability? So that is the value function lies in the span of the features, like, can we do it? So that's the question that we're going to look at next. So in a way, this is more ambitious, but there is usually no misspecification. If there was some misspecification, you can tolerate it, but like the errors blow up.
How pathological are those lower bound instances in the?
That's pretty pathological. Yeah. As usual. Yeah, it's like the lower bound instance on the previous slide. It's just like a big tree, and like it relies on constructing the features. It's basically packing the unit sphere with the feature vectors, and that creates this blow up of the errors. If you have friendlier features, then don't expect this blow up. That result is really about the blow up. That this blow up in the worst case is necessary. Okay. But you can ask the same questions for the coming negative results too. Yeah, that maybe, yeah. Well, I think that they are insightful. Why pathological? All right, so we are done with this, and so let's get to results about this weak function approximation. All right, so as we're gonna see, the single most important determining factor in these results is going to be how big is your action space. So the action space could be relative to the number of stages in the problem and the number of features or basis functions. It could be, you know, like polynomial or much less, like constant, or much more exponential in the smallest of the two. And we're going to see that this determines a lot. So I will call this first two cases the few actions case, and this one is the math one. So let's start with the many actions case. We have already seen this result. So I'm going to build these tables. So there are all these, like, you can choose this, you can choose that, and like we're going to have a lot of fun building these tables. So we have seen this result. This is the Wang-Zhen Ben-Van Roy result from 2013. And just to explain the notations, so the optimal parameter vector lies in this ball of radius b. D is the number of features, h is the horizon, e is the number of actions, and the number of features is assumed to be bounded by 1. And the in the tables, we're going to have source, like how many actions we have, what is the MDP class. So explain this notation. So M is for MDP. These are the parameters. This Q star means that it's Q star realizable. So that means that the features are such that are handed to the algorithm that the Q star function, this optimal action value function, lies in the span of the features. And this intersection is just means that, but this other class, this is all deterministic MDPs. So if you consider only deterministic MDPs and the Q star function is realizable, then this checkmark means that there is a poly-query complexity, in this case also computational complexity algorithm that solves this problem. So that's the first result. So the next result is from a paper of ours that says that if you have a large number of actions, exponential in the smallest of the dimension and the horizon, and you give up on deterministic MDPs, then this nice result is gone. And this is also going to be based on some pathological construction if you want. So that's pretty sad. Okay, so one more thing. So this global access, it just means this generative model. So it's like you're interacting with a simulator, and then you actually know what the state space is. It's like a pretty strong condition. Because when you have, a simulator of a robot, like, what do you know, like which states are legal or how to call even the states? So that's a pretty strong assumption. But for a negative result, we want to have a strong assumption, right? So even if the simulator has global access.
So what is P this?
The transitions, P is transition. The transition kernel can be deterministic, but the rewards can be stochastic. So it's enough to make the rewards stochastic. Of course, you can push it to the other way. All right. And now here is the shock. So if you have any number of actions and you have both V star and Q star realizability, and you have global access, no, you can do it. So that's pretty interesting. That's quite surprising. That's query efficient. It's not computationally efficient. Basically that algorithm needs to kind of like read the whole state space, do a bunch of calculation. It's doing this version space pruning. It's like pretty aggressive, and it really needs this global access. We will see it on the next slide. Right. So I already talked a little bit about these simulator access models, but I just want to clarify it a little bit more. So we talked about this global access. The algorithm gets a description of the full state space. It gets all the features of all the states up front. It can do any computation with it. And some of these algorithms, in quotation mark, do this and can ask for a transition at any state actually. Local access model, I'm going to talk about local access next. It doesn't get the description of the full state space. It's much more realistic. Only gets the features associated with states that are being visited. Simulation always starts at some initial state that you can get back to. And the simulator can be reset to a previously visited state. So there is checkpointing in the simulator if you want. So you can implement this by having a simulator, and then like as you go, like you ask the simulator to stay within internal state, and then later on you say, well, step number 152, when or whatever state you were at, like let's go back there because it was interesting. So that's what you can do with local access.
You said your result was not efficient in the global access model, but what does efficient mean in the global access?
Yeah, I mean, like it could be that it doesn't use global access that way, right? The algorithm could choose not to use all this part. Yeah. Okay. And finally, the weakest of all of these assumptions, online access, which is like when you're interacting with the real environment, that's like what you have. You can't reset back to previously visited states. If you have deterministic transitions, of course, you could do that by saving how you got to some state. But if you have stochastic transitions, then that's not possible. And so again, like we kind of see the difference between stochastic and deterministic environments. Just kind of interesting. Okay, so the few action scales. If you have only a constant number of actions, then we have lots of check marks here. So let me go through these rows one by one. So there is V star realizability, or and under that you can get a positive result. There is Q star realizability, but the transitions should be deterministic. The rewards can be stochastic, no? And so that's kind of like, if your initial state is also stochastic, you kind of like fall that into here. Then you can do it. And if you have V star and Q star realizability simultaneously, so you have two feature sets. So on the previous slide as well, like if you have V star and Q star realizability, kind of work hand in hand. You have two feature sets or two set of basis functions, but this only holds under the states that are reachable from the initial state. So that's a distinctly weaker condition, it turns out, that then assuming that V star, Q star are realizable at all the states. And so under this result also holds under local axis. And now, if you increase the action count, as I promised, the action count determines everything here, to be lower the polynomial of the minimum of the dimension and the horizon, then you get negative results pretty much for all the cases. So you can start with V star realizability and you can slash in determinism there. It doesn't help. Q star realizability, you got the negative result. And V star, Q star, reachable realizability, deterministic transitions, you get a negative result. So notice that, like in the previous slide, we had this positive result on the global axis for the same set, or like under the stronger assumption that V star and Q star are realizable at everywhere.
Give us an intuition of why. Why is that? Like, why does just as much more space of actions cause it to be?
Why the action space?
Yeah, why is it so important to?
Yeah, Lewis. Yeah, Lewis. Next. The next. Yeah. All right. Okay, so I actually want to start with the green rows. Why these problems are not hard. And I'm just going to talk about this setting, and you can generalize this setting to the other settings. I've done that. So we have constant number of actions, we have stochastic transitions, V star realizability, and local access. So the algorithm is going to be called tensor plan. And it turns out that this is kind of like just a slight modification of this constraint propagation algorithm of Jenkman and Bellman-Roy. So we have the same notation, except that now we have not action value functions, but state value functions. You have the TD error, which is the difference between, like how much reward you're predicting to make under this theta parameter versus how much reward you're making. And so this is the new thing. So rather than saying that, well, I would need to know, like, remember in the TD error previously, there was a maximum overreactions in the optimistic constraint propagation algorithm. There is no maximum overreactions here. But what we are doing is that we are taking the TD errors and we're multiplying them all. So these TD errors are just like numbers, right? If any of them was 0, then the product is going to be 0. And the product is only going to be 0 if one of them is 0, right? Like it's pretty elementary. So you can basically rewrite the Bellman equation by saying that under this condition, the product of the TD errors at all the state action pairs is going to be 0, right? Because if you take the optimal action that the optimal policy gives you, that makes the TD error 0. So that's one direction. And in the other direction, if you have this, well, that doesn't quite imply that you have the optimal. That doesn't quite imply that you have the optimal policy. It could be that there is some other policy for which these equations hold, but we're gonna fix that. So there's no problem. All right. And later on, it will be clear why it's advantageous to get rid of the maximum and write this product. So how does the algorithm work? It's basically copy pasting the previous algorithm. We start with the full parameter set. We are iterating. We are going to be optimistically choosing a parameter vector. And after that, we do a rollout. We don't do one rollout because we have stochastic transition. So we do a bunch of sufficiently high number of rollouts. We collect the trajectories. And along the trajectories, we're going to measure approximately the TD errors by using our local access to the simulator. So if you're in a trajectory, you were choosing a state action pair, you need to measure the TD error there. What is the TD error? So there is this averaging happening there. So you're going to use your simulator, reset to the state action pair a number of times, and then you approximate quite closely the TD error. So there we are using very, very strongly the local access model. That you're able to do that. In the online access model, where you can only run trajectories, it would be really hard to get back to exactly the same state action pair. So these are a strong use of simulators. And once you did that, you're shrinking the parameter space. And return if the parameter space didn't change. Or well, it's in the actual algorithm, it's slightly more complicated than that.
You seem to have made a sort of careful choice to approximate the value function and also use a Q function like.
That's right. Yeah.
Is there some insight into why, or?
Well, it's because we want to get rid of the max. So the max is not playing well with all the linearity and everything, and we are going to see that the product plays much better with linearity.
With Q, you have the max.
In the Q, we would have a max, yeah. That's why we can only deal with deterministic transitions when you have Q star. All right. So questions. So why will a tensor plan, this algorithm, stop changing the parameter vector? So if you look at, so why is this product a win compared to using a max? If you look at what this product means, you can write it out as an inner product, reorder the terms, introduce these tensor products. And then what you're going to see is that this can be viewed as a linear constraint on the polynomial of the parameter vector, right? Which is this tensor product of the parameter vector. And so this is a bunch of linear constraints. And so that was why what was advantageous, because we can solve linear problems. Or we know like for how long you can just add constraints and eventually find the solution when you're exhausting all the dimensions, right? So after you adding d+1 over a constraints, then you shrunk the parameter set and you found the solution. So that's why we are switching from the max to the product. And so the other question is, what was the role of optimism here? And I already gave you a hint that the algebraic Bellman equation doesn't go both ways. Like there could be policies for which the algebraic Bellman equation holds, which are not optimal policies. And the way to get out of this, and you want policies which have high value, So a natural choice then is just to be optimistic with respect to the initial state, because when that happens, then you can guarantee that the policy, whenever you're stopping, the policy that you're going to get, if you haven't eliminated the optimal policy, is going to be optimal. I have 2 minutes left. So this is the result that you can prove. And so back to Emma's question. So what's the insight about like why the action set has such a huge influence? We were doing this tensorization, this algebraic trick. Because of that, d to the power of a appears. And you can predict from that that things are not going to go well if the number of actions is going to be higher. Now the question is that really true? So that's another paper. I won't have time to explain it. It's basically an information theoretic argument that somehow having already polynomially many actions in an H horizon problem is going to throw off all the algorithms. Like you can hide rewards, and no algorithm is information theoretically able to find them. All right, so so one slight note about this is that in bandits this is totally not true. So you can have large action spaces, you have a horizon of 1. And disregarding computational problems, you can solve all your own right problems, right? Like near bandits is an awesome topic. Regardless of the number of actions, you can have infinitely many of them. Anyway, so this is the full table. And then there is a question of whether you can get, this is just query efficiency. So when can you do it computationally efficiently? We know that in this case you could do it, and then you should talk to Gaurav. I don't know where he's not at the moment here, but he's staying at Simon's. Yeah, he's been working on this problem. We've been working on this problem, and in short, there are already some results by them published at COLT this year that show that under some conditions, some of these problems cannot be solved computationally efficiently. And the prediction is that, well, unfortunately, this is going to be true for the remaining problems too. Okay. All right. So wrapping up. So Bellman's modest optimism, did it hold up? Well, as far as successive approximations are concerned, it seems that when the algorithms can do something, they're not really doing that. So that's kind of like a very interesting point to me. If you try to do these successive approximation type of algorithms that they were introducing, they incur a lot more errors. So they're blowing up errors way faster than this version space shrinking algorithms. Yet, if you think about computational efficiency, it seems that they're onto something, because the version space shrinking algorithms can only work in very specific cases, and in all the other cases, it's more like a DP solution that we are having. And another big conclusion is that even if you have strong function approximation, you will have to leave this approximation error blow up due to exploration. Unlike in bandits, large action spaces are going to be a nightmare. And I have a bunch of open problems, but I just stop here. All right.
Like one question. Could you say a little bit about the open problems?
Yeah. So yeah, it's given everything that was built up, it's very easy to state them. So we don't know whether the query complexity can be kept polynomial. In this case, when you have Q star eligibility and you have constant number of actions and the transitions are stochastic, we only know this a positive answer for deterministic transitions. For stochastic transitions, just leave it us. We have no idea. It's very intriguing. The next one is what is the computation complexity when you have constant number of actions and you have V star, Q star realizability globally. The next one is that if you have online access, so you don't have this QPy under QPy realizability. If we had global access, or we have a newer paper that says that if you have local access, then you can get everything polynomial time, and like it's beautiful. But we don't have the same result for online access, which is kind of the real deal if you're interacting with a real environment. So maybe there is a separation between when you're interacting with a simulator, even if it's just provides you local access, it could be that you can solve some of these problems and you can't solve them if you only have online access. And then like there are vaguer open questions, like how to deal with nonlinear functional approximation. And Bellman's paper obviously was considering continuous action spaces. Okay, there was a lot of other structure there, but clearly from this work, if the number of actions is exploding, in the worst case, like nothing can be said, but that can't be the end, right? Right, and then it seems deterministic dynamics is helpful. You can do things with this factorization. I don't know, like these are vaguer open questions. The first few are, I think, pretty good. Okay. Thank you. If you want to
Back here at 11:15.